Hello again, everyone. Welcome to part 2 of our screencasts on hypothesis testing for a single population proportion. We'll begin by discussing the topic of the relationship between confidence intervals for a proportion and hypothesis tests concerning a proportion. So, thinking back to our first example from the last slides, when the sample size was 50 people with four-year college degrees, and the sample proportion was 24%. If you were to take that data and to make a 95% confidence interval, as we have learned how to do, it could be done through the code that you see here. And the lower bound would be about 12%. The upper bound would be the sample proportion plus the margin of error, about 35%, 12 to 35%. And notice two things. The p-value for the hypothesis test for this situation was 0.16, which was above our alpha level of significance of 0.05, so we weren't going to reject the null hypothesis. And notice that the confidence interval that we just made, the 12 to 35%, contains that null value of 33%. So we were not rejecting the null, and the null value is within that range of values that the data say could reasonably be values for the population proportion. We did not reject. Null value was reasonable. But now let's think back to that second example where the sample size was 200 and the sample proportion was the same, 24%. So if you make a confidence interval for this situation, the only change being the sample size here, then when you go for the lower bound, you get 18%, and when you go for the upper bound, you get about 30%. So I'd like you to notice these two things. The p-value was very small, and indeed it was less than 0.05. I think the p-value is actually more than 0.0002. That may be an error. I think it was like 0.005. And the confidence interval, 18 to 30%, does not contain the null value. So we are going to reject the null hypothesis, and the null's value is not reasonable based on the data. It's not inside the interval. This totally makes sense because of what confidence intervals are trying to do. A 95% confidence interval is supposed to provide a range of values for the population proportion that are plausible based on the data. And so what we're seeing is that when the interval contains the null value, the test of hypothesis that we do is not going to reject the null hypothesis. But when the interval does not contain the null value, then in our test of hypothesis, we will reject the null hypothesis. That's always going to happen for this kind of test, this perfect correspondence between confidence intervals and the results of the test. I do want to emphasize some notation for the null value. You know, when you read the null hypothesis, it's written like H naught, P equals 1/3. And that particular value that the null believes in, it's called the null value in the textbook, and I'm using that terminology here. And you'll see it written as P sub 0 in the textbook, and I'll probably be using that too. Another topic for this screencast is the topic of making errors. You know, our methods, like our confidence intervals, they attempt to provide, this range of reasonable values, but we have seen that sometimes confidence intervals don't contain the population parameter that they're trying to give you some idea about. And that's by design. We designed it so that 95% confidence intervals for P would contain P about 95% of the time in repeated sampling. But that means that they're going to fail to contain the population proportion about 5% of the time in repeated sampling. There's nothing wrong about that. That's just how they're designed. In general, if you make a confidence interval of any particular level, say choose a number alpha between 0 and 1, and you make 100 minus alpha % confidence interval, then it's going to fail to contain the population proportion 100 times alpha % of the time in repeated sampling. So like if your alpha is 0.05, then the 100 times 1 minus it turns out to be a 95%. And you'll be failing to contain the population parameter, 100 times 0.05, 5% of the time. But it works for the other levels too. Like if alpha was 0.10, you're making 90% confidence intervals. They're going to fail to contain about 90% of the time. So we're familiar with this idea that confidence intervals are designed using formulas where there's an expectation that they're going to be, quote unquote, bad intervals a particular percentage of the time in repeated sampling. Tests of significance are designed the same way. When you make that decision whether or not to reject the null hypothesis, sometimes you will make the wrong decision. You may never know it because you're not God and can't look into the whole population, but sometimes you'll be making the wrong decision. And so there's names for the types of errors you might make. See, there's actually 4 possibilities indicated by this table here. It could be that the null hypothesis is true, and it could be that the null hypothesis is false. And based on your data, you may end up rejecting the null hypothesis, or you might end up not rejecting it. Now, if the null hypothesis is true and you don't reject it, then that's okay. You have not made an error. You won't know that you're right because you don't know the population parameter, but you will not have made an error in that case. Similarly, if the null hypothesis is false and you reject it, then you're okay. But in the other 2 cases, you've made an error. If the null is true, but you reject it anyway, that's called a type 1 error. If the null is false, but you don't reject it, it's called a type 2 error. Type 1 error, where the null is true, but you reject it, is kind of like what happens in the judicial system when the defendant is actually not guilty, but gets convicted anyway. And a type 2 error is kind of like what happens in the judicial system when the defendant is guilty, but the jury does not vote to convict. You can put numbers to how much it's designed to be wrong. If the null hypothesis is actually true, and if you set your cutoff value to, say, 5%, then In a well-designed test of significance, you're going to end up committing a type 1 error about 5% of the time. It works for any level of significance, any cutoff value that you choose. If the null is true and your cutoff value is some fraction alpha, then about 100 times alpha percent of the time, you're going to commit a type 1 error. The notion of type 2 errors, that's when the null is false and you didn't reject it, is useful in thinking about what we call the power of a test of hypothesis. The power of a test of hypothesis is the probability that the test is going to reject the null when the null is in fact wrong. That is, when the null is wrong, the test sees that the null belief is unreasonable. Mathematically, it's expressed as 1 minus the probability of a type 2 error. So the power is a kind of probability, and it turns out that the more the null value differs from the real value of the parameter, that is, the more wrong the null belief is, then the higher is the probability that the test will lead you to reject the null hypothesis. That is, the more powerful the test will be. Another thing is that the bigger the sample size, the more powerful the test is. It's kind of like a microscope. You're looking at something under the microscope, and say that two little microscopic creatures are only a small distance apart. But if you make the microscope very powerful, if you zoom way in, you can see the difference between the two. It's the same for a test of significance. If the real value of p is in one place, and the null's value of p is in a slightly different place, when you zoom way in with a big sample size, you'll be able to see that difference. Mathematically, we can understand why this is so because of the math formula for our test statistics. Think about the standard error for the sample proportion. It's got the sample size in the denominator. When the sample size is big, that fraction inside the square root sign is going to be small. So the standard error is going to be small. And then when you go over to compute the test statistic, you're going to have a small number in the denominator of the test statistic. So that means the test statistic is going to be big. And so that means that when you look at the area under the standard normal curve outside the test statistic, there won't be much area. And of course, that means that you're going to have a small p-value. And the smaller the p-value, the worse it looks for the null hypothesis. Therefore, the more likely it is you're going to reject the null hypothesis. Now, it would be nice if we never made errors, never made type 1 errors, never made type 2 errors. That would be wonderful. But how do you cut down on the chance of making those errors? If you want to cut down on the chance of a type 1 error, where you're rejecting a null hypothesis that was true all along, then you could do that by setting your cutoff value alpha really low. Like instead of 0.05, make it 0.000001. And then you have to get a little teeny p-value in order to reject. But then, if the null happens to be false, you've made it really hard for you to reject the null hypothesis, so you're going to make those type 2 errors become more likely. And on the other hand, if you want to cut down on the chance of type 2 errors, if you want to make your test more powerful, you could set the cutoff value alpha really high. And then when you get a p-value less than that big alpha, you get to reject, you know. But that means that when the null is true, you're going to make those type 1 errors become more likely because you've made it more easy to reject. So life is hard, and then you die. There's just no way out of it. The only way to make type 1 errors less likely when the null is true, and to make type 2 errors less likely when the null is wrong, to do that at the same time is to set your alpha very low and increase your sample size in really high. But that means that you're going to have to work with very large samples. And that's time consuming and expensive, to gather a whole lot of data. So there's really no way out of it. You're going to experience type 1 and type 2 errors. You're never going to know, in most practical circumstances, whether you've made them. But because you know something about the rate at which they occur, then you can factor that in, kind of control how it helps you understand, interpret, and use the results of your data analysis. That's it for the second screencast. In the third screencast, we're going to do another look at the hypothesis testing process and break it down into a series of standard steps. That's all for now. See you soon.